这样还没有。
Okay, good afternoon. We all start our colloquium, joint colloquium, and now thank you for coming. Today we are very pleased to again invite the NTU graduate, Professor Wei-Su Ho. He graduated from NTU some years ago, and then went to UCLA, had his PhD, and then moving around in Europe, PSI, Munich, and then come back to Taiwan. Still years ago, he has been doing trained as a theorist, has done many interesting work. But then after he come back to NTU, he start to think maybe the experiment is equally important. And amazingly, he was able to make both theory and experimental contributions in a significant way. So he built up the NTU HEG group. So today's talk maybe touch both how the theory goes and how experiment might search for many of the things. So he's now a national chair and lecture professor at the NTU. So he's on the 5th floor. If you have more questions, you can hunt him and there on the 5th floor for other continued discussions. So for now, let's welcome Professor Wei-Su Ho.
Thank you, Xiaogang, for the introduction. Okay, are there any astronomers here? Oh, okay, thank you. I particularly chose this picture such that we are together. And also, you know, in the abstract that was sent out today, I did put in matter dominance of the universe, trying to connect. It is a theme. Actually, before I started, the chairman already asked me, what does whither mean? So to answer that question, I'll first explain the title. By the way, this dictionary, Pictionary, I think we're familiar with in Chinese, 说文解字. Wen is actually Pictionary. 字 is made of wen. Okay, this is one single wen, and this has two pieces. Okay, so I'll introduce the title, and then, you know, within the title, there's Yukawa couplings, extra Yukawa couplings, and then section 4 and 5 can be viewed as the main content, why I'm giving this this talk and so on. Okay, so that's the outline. Well, with the new physics, I don't know whether that's truly proper, but whither is like to where or where to. So it's like, where should new physics go? Where do we go to find new physics? That's my meaning. So I put new physics in quote unquote because in most fields, there's no new physics. Okay, there's no new phenomena maybe. But here we're talking about new physics, and it means something beyond the quote unquote standard model or defined standard model using a recent essay from Weinberg. Okay, finally, Yukawa couplings. Now this you should know because it's part of our culture. It always amazes me that when in the early 30s, the center of physics was in Europe, and it took a young Yukawa sensei in the Far East to point out that the confined nucleus is because this pion exchange, because the pion is heavy, unlike the photon. So this pi-N interaction is the original Yukawa interaction. So a third of a century later, it was this Weinberg which put together, if you look at pi and n, the nucleons are spin 1/2, and the pion is spin 0, and it's a pseudoscalar. So what Weinberg put together is a scalar fermion-fermion interaction, which we'll turn to. But before that, so let me now turn to standard model. Well, Weinberg actually looks a little bit older than this now. The standard model, we'll just call it SN. So let me read it. A quantum field theory. Here, we're not going to teach you quantum field theory, don't worry. A quantum field theory successfully accounts for strong, weak, and electromagnetic interaction of known elementary particles. So this is particle physics. Now, everybody should be familiar with E&M. Weak and strong is roughly in the realm of elementary particles, but it matters elsewhere as well. So that's my introduction to standard model, not more than this. We'll come back to Weinberg soon. He received the Nobel Prize in 1979, and this half a century, yeah, he's a big player in it. So the last piece of the standard model, you must have heard this story because I was standing here some time ago. Actually, this picture was taken just about half a year before the prize announcement, and actually was taken in Stockholm. So I think this was my ticket to self-invite to give this, not the Nobel lecture, but the lecture on the Nobel, okay? So, but the point here is that the Higgs boson was found in 2012 and received a 2013 Nobel Prize. But actually a year before, the Higgs was actually found. I was very impressed in a summer conference by this slide, by this Dr. Bashaku. So basically he said, no hint of new physics in the OHC data. So 2011 was yet, and I add to date. So in the last almost a decade now, at CERN, at OHC, there is anxiety, we have to admit. If particles like these existed, we should have discovered them, okay? So let's take SUSY, for example. SUSY, I'm not going to explain it, supersymmetry. So take SUSY, well, there's no hint of it. So even I cannot read this too well. I don't know, this projector must be too old or something. If you were in the middle, so in the interrogator, if you were in the middle of the room the whole time, why can we not find a single witness to corroborate your testimony? Okay? Now the judge is sitting here. The judgment has not been really given yet, okay? But what I write down here is that it's not just, the gray, blue elephant that's being interrogated. Also white elephants, pink elephants, hairy elephants, a list here, okay? So we have not found these elephants in the room. We found an empty room. But search continues because verdict has not been placed. Just not found, okay? So I say, well, search continues, but cracks. Well, this sounds sarcastic, but to be sarcastic, there are also dotty elephants which can hide in cracks and not show up in the room. But anyway, so the 1, 2, 3, 4, 5 here, different kinds of cracks, is meant to match these 5. So this is an actual search result last year from Atlas. There's corresponding results from the CMS experiment, which NTU is in. Now, don't underestimate the effort. Each bar here, Atlas has about 3,000 people, so each bar here probably is a year or two's work of more than a dozen people, okay? But so the search would continue, but we just continue not finding it, okay? So let's step back and look at ourselves. We are made of this column, what I call quote unquote us. So the U and B quarks are bound by this gluon, the strong force, the strong interaction into nucleons and pions. The pions binds the nucleon into the nucleus. The nucleus, carrying a lot of positive charge, attracts the electron, and that's us. Now, we're not really made by neutrinos. However, without the neutrino and the weak force associated with it, the sun will not shine and the earth will be dead cold. No life, no life. Okay, so we're blessed with this neutrino. The strange thing is, there are two things that's strange here. One thing is that there are 3 copies. Now, by 3 copies, I don't mean 3 copies of us, because that's the other strange thing, the origin of mass, because when you go to the right, these guys are just heavier. So when they're produced, or in the early universe, they just decay away. So the origin of mass is the Higgs affair. And in particle physics, this box here, the masses are all explained by the Higgs particle, the one that we discovered. So it roughly goes as follows. You must have heard the Higgs mechanism, the Meissner effect, the plasma picking up a mass, and so on. So you have a so-called doublet field. Here there are actually 3 particles. Z is neutral, but W is charged. So it's a pair of charged particles. This triplet gets mass because this doublet is really the same symmetry. The real field develops a so-called vacuum expectation value. The actual value is about 246 GeV, tremendous, okay? This G is the weak force that induces neutrino emission, embedded decay, and so on. This G is about 0.66 or something. So you can see that we have observed these particles 80 and 90 GeV, and that rhymes with this 246 GeV. Now, whether it was intended or not intended, we discovered, or someone uncovered for us, that masses are all dressed up couplings. So here, this is the weak interaction coupling, times the scale. Here, as if people cheated, invented another parameter, multiplied the scale, copy from here, okay? But that really is what happens, and this is the Yukawa coupling, okay? So the origin of mass is dynamical. So this is, well, Weinberg had many famous papers, but this turns out to be the most famous. That's the one that got him his Nobel Prize. So you see this, the notation is mildly different. This L is a doublet. This Higgs field is a doublet, we've seen that. And then this one is called a singlet, okay? Now, if you look at these Lagrangian terms, the A vector, that's a 3, and also a vector index, so 3 bosonic vector fields. And then there's another one, B, so it's 3 plus 1. And it's the symmetry breaking, this VEV, this neutral field, developing a vacuum expectation value. So you see, charge is protected, and that's why QED remains. Now I guess I can project and remark saying that if you think about someone like Weinberg, he's the disciplined, diligent, good student. What do? They follow all the rules. They turn in the homework and so on. So he famously added this term because the rule is, for the Lagrangian, whatever is allowed, whatever is not forbidden is allowed, okay? So he put in this term, and this is our Yukawa coupling because this is the fermion, and this is the boson, so that's a fermion, boson, fermion term in the Lagrangian. And when this phi develops a VEV, you get a mass. So this is how this thing first appeared in human literature. Okay, I've defined it. Every mass, the fundamental ones, not the proton mass. Proton is another story. Every fundamental fermion mass multiplied by square root of 2 divided by 246 in the GeV units, you get a coupling constant, okay? So now we're entering Yukawa couplings. And this is a spectrum we have observed. We said 3 copies, electron and UD were composed of, neutrino, very important. here gives the dates of the experimental observation. So I put the word heavy flavor here. So these are called heavy flavor. But I also put the dash here. The S quark and the muon were known much earlier, okay? And their behavior are somewhat analogous to these heavy flavors. And I will call myself a heavy flavor physicist, okay? So these are the fundamental fermions. Fundamental is equivalent to elementary. We don't know whether they have a structure. We don't see a structure, okay? Okay, that's a side remark. So this is the scale of mass. Electron is 0.511 MeV. And then normally you need to divide by c squared, but not in particle physics. Okay, the big but unnoticed news last year was that the humankind, so this was like 2015. It's very close, but we could not claim. It's not yet fully done. But if you look at the error bars here, this linear relation, now bosonic fields, you need to massage it, take a square root something. This linear relation is what we saw in earlier pages. We have confirmed it for the heavier ones that are more strongly coupled, okay? So it's really a very significant step for humankind, because I'm in flavor physics. We know some of these by indirect methods, but this is direct production and decay, and we measure the cross-section and they fit this curve. So at the end of August last summer, I did put out a press release from NTU press office. Not a big deal to make a hoopla, but it's kind of a record, saying it's a significant step. We've passed a milestone. But my point is also saying the dynamical behavior is experimental fact, okay? This is not just a mathematical formula. We have used all the dynamics to explain what we observe, okay? So now let me go one step further. This summarizes all weak interactions, at least for the quarks. So this is a weak interaction coupling. It looks a little bit complicated, but think this way. Think of this as an electron, photon. That you should be familiar with. That's how, that's the fundamental interaction in QED, how an electron emits a photon. Here, just saying a down-type quark has charge minus 1/3, can turn into an up-type quark which has charge plus 2/3, and emit a W minus, yeah. The significant thing is that this W is massive. So even if you have not worked it out, you must know that the photon is massless. It moves fully relativistically. Well, not just fully, it moves at the speed of light. You cannot catch up with it, so it has only 2 degrees of freedom. It has only 2 polarizations. So it doesn't work for the W boson. You can catch up with it, so it has a third component called the longitudinal component. Now, the Higgs mechanism goes this way, saying that the longitudinal component took the symmetry broken gauge boson, vector scalar field, and made it into the longitudinal component. Is called, the gauge boson has eaten the scalar field. But here I reverse it, saying this is all we need to know. We only need to know G. If you know a little bit about propagators and how longitudinal degrees of freedom propagate, you can derive this thing on the right-hand side. So they're the same thing, okay? But the masses appear because these are now physical states that we have observed, okay? So I stress again, masses arising from coupling is not a concept. It's a dynamical coupling that we have measured. But here I need to expand a little bit. We said there are 3 copies, that they're indexed I and J, and they run from 1, 2, and 3. And then I have down-type quark, up-type quark, and also charged leptons. So I have 3 types of charged fermions, and each of them have 3 copies. So the I and J each run with 3. So actually, it's a Yukawa matrix. The dynamics is a matrix. And we diagonalize that matrix to get our mass eigenstate, okay? But in so doing, something remains. This Vij here is, roughly speaking, the difference of part of this diagonalization, difference between the up type and down type, because this is down to up, okay? And it took two young Japanese in late 1972, when Kobayashi was not even 30, to demonstrate. You know, that was a time when even the second generation, the second copy, was not yet fully known. So they invented the third copy before it was even known, by showing that a CP violating phase appears and you have CP violation. CP violation was experimentally observed in 1964. So that was the motivation. So by using, well, not by using, these are unitary matrices, which I'll come back to. Okay, I just lectured you, just telling you that these things emerge without going into any details. So Kobayashi and Masukawa received the Nobel Prize in 2008 because of the previously cited work. So this was confirmed at the B factories based on these developments, which I won't get into. So here you see in this black triangle here. So what is that triangle? It's called a unitarity triangle. If you remember, the matrix V is unitary. Okay, I only said so. But by unitary, you see this is VV star, right? So it's VV dagger, and U, C, and T, you just view it as 1, 2, 3. So they are summed over. And D and B, just view it as 1 and 3. So this is VV dagger, 1, 3 element. But since VV dagger, if it's unitary, it's unit matrix, so it vanishes when it's off diagonal. So, but on the other hand, these are numbers. Okay, the matrix elements are numbers. So these are 3 complex numbers. I said there's a phase, it's unitary. So 3 complex numbers sums to 0, that's this triangle. So I call it geometric representation here. So how did Kobayashi Masukawa get the prize? The thing is, we built the B factories, which that's how I started the experimental group here, by joining one of the B factories. And in 2001, we measured this angle, which is this angle. I'm not going to explain it, but I pictured it out. It's the phase angle of this element product. And by this measurement in 2001, we basically confirmed that the physics we study of CP violation at B factories confirmed the Kobayashi-Masukawa extension back in 1973. But besides recounting this history, what I want to bring out is it's not a bombshell, because it's well known. Actually, when we were doing a Bell experiment, constructing Bell detector, and before data taking, at least I myself had a strange sense saying, yes, we're going to confirm or refute Kobayashi-Masukawa, but especially if we confirm it, we discover CP violation in the lab, but we'll demonstrate for sure it's not sufficient for the universe, okay? Basically speaking, just saying all these are a product of suppression factors. I'm not explaining Yaoskog invariant, but just letting you know that it's 100 billion, 10 billion times falling short. So I have a cartoon here. So this CERN guy says to the clerk, lost and found, antimatter's gone missing. So the clerk, sleepy-eyed, says, when did this happen, sir? About 15 billion years ago. Okay, so let me show you. I've been teaching a general education class, so I steal my own slides. I forgot to tell the TA to turn on the mic, but it's okay. So let me explain. Big Bang. That's how the universe started. But very shortly after, we are left with matter, okay? Antimatter disappeared. Now, so the thinker is sitting here, but that's not quite true. We're not thinking outside of space-time, okay? We think 138, well, E, okay? So 13.8 billion years after creation, okay? We sit here and think. And we think, and of course, we are handyman as well. So we think and build machines, and we understood this. Now, of course, that's the mystery of disappearance of antimatter in our universe. But I put the mysterious here because since this is also a general colloquium, I would say we humans existing so far down the line to be able to comprehend all this and call this mysterious, that's even more mysterious. Got that point? Okay, but it's to introduce the fact that we don't have antimatter in the universe. And that was partially the talk last week. Okay, so Yukawa couplings, we have measured the masses, we have measured further the remnants in that matrix V. So what do I mean by extra Yukawa couplings? So that's what I'm going to turn to next. And the bottom line is that it's an experimental question. Okay. Now I recycle an old slide once again. I would say I'm bothered to treat all the way back to Big Bang, the Higgs field or Higgs boson that we have discovered. I'm bothered by it because fundamental is a strong statement. Fundamental by theory, that's your business. But fundamental drawing this figure, I'm bothered by it. But that's not my theme today. Today, I'll accept it, okay? The point is, if we have a Higgs doublet that is fundamental, that has undergone symmetry breaking, and the fact that actually we don't see anything else, then it really highlights that a second Higgs doublet is highly plausible, okay? Now, if you have a second Higgs doublet, so you have phi 2, then a la Weinberg's paper, there should be another set of Yukawa couplings, okay? And it should be highly motivated because we have measured Km. We show both from Km and masses and dynamics that Yukawa couplings are real, okay? They are there. We know they are too small to explain the universe. So extra Yukawa in this setting is the natural way to go. But very few people, except just writing another paper, think deeply about this. And the reason behind is Weinberg and his classmate, they were high school classmates, Sheldon Glashow, they received the Nobel Prize together. In 1977, 2 years before their prize, wrote a also very famous paper, basically stressing this natural flavor conservation. Now, if you're trained in the modern age, whenever someone sells you, this is all natural product, you should be careful, okay? So I hope you pick that up. It's very famous, it's very well incorporated into the mindset. So let me review that. So this is the one Higgs field. Now, these are complex Higgs fields because we need to manage charge. So there are actually 4 fields here. The real field, a real neutral field develops a VEV, so 3 fields get eaten into the W plus, W minus, and Z boson, longitudinal components. But if I add a second doublet, again, there are 4 fields, so there are 4 additional Higgs-like objects. 2 of them are charged. One is just like the one we observed, this real field here. The other one is so-called imaginary, the pseudoscalar. So in this context, what is Glashow-Weinberg NFC condition? Basically, the target is that you have only one Yukawa matrix per mass matrix, okay? So uptight quarks, you allow it to couple to only one Higgs doublet. Likewise for down-type quark. Now, if you have 2 doublets, there are 2 ways to do it. So there's model 1 and model 2, okay? But by enforcing this, There are no extra Yukawas. The Yukawa couplings are all from masses, mass divided by VEV is your Yukawa. So this is just like in a standard model. Some parameters exist. And the strange thing is that it automatically, this automatically is satisfied with supersymmetry. So with the popularity of supersymmetry, it was a happy marriage that this became a reference standard. Now, when we discovered the Higgs boson, it was not yet known, but after several years, one thing emerged. We found that this boson does not seem to feel the existence of a second doublet. It seems to reside in this doublet that generated the VEV, okay? Put another way, the observed boson is very standard model-like. It doesn't seem to mix with the extra doublet. So this phenomena has been called alignment. I'll use that. What does alignment mean? This observed field seems to align with the field that generated the VEV, okay, in certain language. So it's not so easy to remember this, but just saying we don't seem to have any indication really of the second doublet. So let me come back to this now. So we've discussed Glashow-Weinberg NFC, but just a year after Glashow-Weinberg's paper, Harold Tritch noticed something, which after 5-6 years, Cheng and Scher picked up and put forth some idea. What Tritch noted was that from the D quark and strange quark mass, taking some square root ansatz like this, he could cook up the so-called Cabibbo angle, the first rotation angle. You don't need to follow fully that. But just saying this square root behavior linking masses and this mass mixing relation, these are empirical facts. We have seen, I hope you noticed, that we put on the log scale, the U and C and T masses were like this, right? So they're orders of magnitude apart. If you take, so VUB and VCB, these are the CKM, the matrix V element. So these were measured around 1983, first measured. And they turn out, especially when you square them, to be far less than 1. And also, this one is far less than this one. So this information is roughly encoded inside here. And that was the Cheng-Scher proposal. So the proposal was saying that, I forgot to say this important line. Sorry here. What were they afraid of? The thing is, if you have a second set of Yukawa couplings for each mass, then the Yukawa couplings cannot be both diagonalized, okay? And then you have off-diagonal terms. And Glashow wrote a famous paper in 1970, part of ingrained into the standard model is why is there no flavor-changing neutral couplings? Now that was dealing with somewhat different subject, but here is the flavor-changing neutral Higgs couplings. So that's why I use the word edict, okay? Dictatorship. This is the way, okay? So what Cheng and Scher said was that, well, flavor-changing neutral Higgs couplings may not be that bad because this kind of a behavior, if you encode it, if both Mij are somewhat knowledgeable about this mass mixing relation, then they will help you control, the nasty flavor-changing neutral Higgs problem, okay? Okay, so a few years later, my take was two things. First of all, jumping and say, well, if what they said is true, this square root behavior, then the largest dynamics is MC times MT, okay? So this is the thing to probe. Or two things. Secondly, I call this model 3. So some people call this model 3. But I would say in a broader sense, it's not exactly the square root behavior, but the mass and mixing seems to be information encoded in the Yukawa couplings that nature provides us, okay? Now, all these were, I would say, just game playing. You know, theorists write papers like buying stock, right? I put some money here, put some money there. This guy owns a lot of stock. Okay, in 2012, the Higgs boson was discovered, and my mindset somewhat changed. Of course, I was pushing the same thing. However, I think my mind turned philosophical. Although I did not fully appreciate it back then. In a way, it's another paper, but it was philosophical, just saying we should really take these off-diagonal elements more seriously, and also parameterize them. The other thing is actually I learned from literature, more carefully thinking, this mixing angle comes in. The off-diagonal behavior is actually from the field that does not generate the VEV. So this standard exotic mixing is a control parameter. And I'll show in a few pages down that the alignment phenomena, that this thing is actually small, is a better mechanism than that square root behavior, okay? So, but I really started to take extra Yukawa couplings more and more seriously. So now let me give you the line why it's an experimental question. It in part goes back to the previous mentioned paper, but imagine you're an experimentalist. So we found the 125 GeV boson. We already have found the top quark decades before, charm quark even earlier. So this is just putting three sticks together, right? Top may decay to charm and Higgs. So can anybody stop me from measuring it, searching for it? No, I cannot. You cannot, okay? I say young and old because I salute Daniel Fournier, because I learned they were a French group who did the Higgs to gamma-gamma discovery, and then he was thinking, and he turned to search for this, okay? So suppose Xiaogang tells them, I shall not do this because you're not going to find it, because Marshall and Weinberg has said it's impossible, okay? But whether you're the young or old, you would say, first you would say, what? I didn't know. Then you would say, since I can do it anyhow, this is great. Because if I actually find it, I shoot down Glashow and Weinberg, I win, okay? If I don't find it, it's a PDG entry because it can be done, okay? It's information. So I'll skip these and just say it's an experimental issue. Once we have seen the Higgs, these three pieces stick together, and whether it exists in nature or not is an experimental question. It's not a theoretical question, okay? Okay, with the limited time left, I'll quickly go through. So as I said, writing theory papers is a little bit like buying stocks, okay? And but the game changer here is that, okay, the analogy stops here, because when you start to really believe in a certain stock, I think that's the end of your investment, right? Maybe that's a trap I'm falling into, but I am known to be a fanatic once I get a little bit stuck in my mind, okay? So I mentioned two papers published last year. One touches barogenesis, one comes back to alignment. Let me quickly go through them. Before that, let me go through the steps just to show you that you have a Y1, Y2, two Yukawa matrices. This linear combination, you diagonalize, and that's the standard model behavior, okay, already measured. However, if you have a second doublet, there's an orthogonal combination to this one, which you cannot expect to be diagonal by the same transformation, okay? And this is the Flamer changing neutral Higgs couplings. So when you follow these steps, this is the Yukawa coupling of the small H field, big H field, the big A field. There's also the charged Higgs field I didn't write here. But now you get the point. This is the physical basis, assuming there's no CP violation that mixes H and A, for instance. We know we're not far from the alignment limit. So these terms are small. So this little h really just behaves like the standard model, okay? And The offending flavor changing coupling is assigned fully to its origin, the heavy fields, the exotic fields. So this is what I mean, that alignment now overtakes Glashow-Weinberg. It can be put away. The thing is to understand alignment, which I'll get back into, okay? And I'm getting more and more interested in these potentially largest extra Yukawa couplings. This is a technical thing, let me not get into. So let me first turn to electric barogenesis. If you want to read, it's this paper. Okay, I'm not going to go through this. Two things I want to mention. One thing is that you need first order electric phase transitions, basically bubble formation, okay? This is the usual law. After the Big Bang, as the universe cooled, symmetry becomes broken, and the broken phase, it becomes an expanding bubble, and we are part of that bubble, okay? So the bubble wall, excuse me, sorry. The bubble wall, scattering across the bubble wall is where you have to accumulate the baryon number. So what I've written here, baryon asymmetry of the universe, quite often called BAU, Bao, okay? Or American Bohr. So this is the baryon number that you accumulated, that you have accumulated ratio with the entropy, basically the CMB photon, okay? So as I said, we are not going to go through this. There are technicalities, which I'm not an expert. I'm more a flavor and CP guy. So across the bubble wall, what you do need is CP violation, one of the Sakharov conditions, okay? So the CP violating top interactions is what matters. And you get some invariant combination like this, the two Yukawa coupling matrices. At the end of the day, you can show that the largest contribution is of this form. Now, YT, the top is 173. Multiplied by square root of 2, divided by 246 is as close to 1 as you can get. So that's one combination. Rho TT is sort of the orthogonal combination going through the same transformation as for getting this quantum number, eigenvalue. So they're both order 1. So you remember that Yaoskog thing, I said there's a lot of suppression factors. Now you can see directly that there are no suppression factors. So I was really impressed that we found a very robust mechanism for BAU generation, okay? So what is plotted here? This is rho TT from 0.01 to 1. This is the baryon asymmetry compared to the observed. So it's robust in the sense that this is about 40 up here for 1. So 0.1, it's still a handsome factor, okay? Now what is plotted here is that the purple ellipse is the other parameter rho TC, let's say is below half. I call that small-ish. And above 1/2 to 1, I put it as the green crosses. There's no obvious difference between the ellipse and the crosses. So that's the statement here. Rho TT is the driver, not rho TC, okay? However, since it's proportional to the strength of rho TT, if I dial rho TT away, now I pointed out, you see there are green crosses jumping above this line here. So what does that mean? It means that if rho TT is small, accidentally, so long that rho TC, because the green crosses means that rho TC now has to be large. And also you can check that the phase of ITC is approaching maximal. Then you can still you can roughly account for the observed baryon asymmetry of the universe. So there are other detailed things, let me not go through. So I'm pretty proud of this paper because it's pretty amazing. I have tried attacking baryon asymmetry before, but this extra Yukawa coupling, this rho TT that I've been keeping on showing you, does the job, okay? So let me come back to alignment. I put it as gray and fuzzy because that's how it is. People don't talk too much about alignment. It seems to be mysteriously there, okay? At least to me, that was the case 2 years ago. So I started to be interested in alignment, just what is behind it at the end of 2016. So in May of 2017, I was visiting Edinburgh. And I remember a train ride from Glasgow to Oban. Well, originally I was going to really have a good time at the distillery there. But I ended up visiting Iona Abbey. So I call this trip, from spirits to spiritual. Okay, I have a slide for that, but I will not show it. But on the train ride, it's a scenic train ride for 4 hours. But we professors cannot just sit there for 4 hours and watch the scenery, right? So I was interested in alignment, so I took papers around. What I picked up, Harry Haber, a friend, is the world expert on extra Higgs bosons. So you can see this is the two-level problem, 2 levels and a coupling. And this is the 2-level formula, mixing. This is the level spacing, and this is the coupling, okay? So to have vanishing mixing angle, one way is to let this level spacing become very large. If they're so far apart, they just cannot jump across, so there's no mixing. Or you let the numerator, this coupling, be weak, then the 2 states do not transit to each other, okay? So that's very familiar. I'm trying to connect with you. And what Howie says is that you need Z6, this coupling, to be very small to account for the alignment phenomenon. So this was in my mind, and all I decided was to cross-check numerically. And the statement is that from their statement, alignment looks like fine-tuning, okay? I have level spacings, but these parameters are similar. But my off-diagonal term, I just pull it down to 0, okay? Clearly, I'm not going to go through this for you, don't worry, okay? But just telling you that this is the 2-doublet Higgs potential, this is the 2-doublet little h, capital H mass matrix, very similar form, but let me simplify. We already know empirically that we're close to alignment. This mixing angle, the mixing angle between the 2 states are not large, okay? So we can look at this thing. This is 2 sine times cosine. When cosine is not large, then sine gamma is closer to 1. So you factor that out and you get that formula on this previous page, okay? Same formula. So all I was checking was that I had the impression that eta 6, I call it eta 6, I was just wanted to know. I actually used not my laptop. I just use this, okay, and generate a table, and immediately found that you don't need tiny eta 6, okay. So then I contacted my postdoc. We produced this plot satisfying some constraints. Let me put it this way. Suppose this eta 6 parameter, you tune it to 0.25. Now 0.25 is closer to 0.1 than to 1, okay? That's the order of magnitude. Then you are constrained to a tiny parameter space. Eta 1 is the lower mass, okay? Eta 1 has to be very close. Oops, sorry. These buttons, too close by. Eta 1 then has to be very close to generating the Higgs mass. But I give you a counterexample. I've already put eta 6 can be order 1. This is truly order 1 now, okay? And I choose, well, to satisfy constraints, eta 1 is slightly smaller. But eta 1 is much larger than this 0.26. But I still get this little h eigenvalue. What happened? Level splitting. No, level repulsion. You had energy levels that were somewhat apart. But if you have a large mixing term, you push the lower state lower. Well-known thing in any lab, okay? So I found this quite remarkable, just saying that this is like the conceptual space for most people, at least I was influenced that way. But the actual space is not only much larger, but allows order 1 couplings. Now, I didn't put down, but if you remember, the order 1 coupling of these Higgs-Ove coupling terms was a precondition for the order 1 phase transition needed for the barogenesis, okay? So again, I was very amused by this, that we can be near alignment, meaning cosine gamma is small, but it does not imply a strong bound on the quartic terms in the Higgs potential. It's a point that's not so hard, not so easy to get across. Okay, let me wind down, time is up. I think theory without falsifiable predictions is not very useful, okay? That's called physics. So I give you 3 examples. So I turn to new phenomena. There are 3 papers. One has not yet appeared. One appeared just last week. So the reminder is that alignment, where we live in near alignment, then NFC is not really needed. But because of that, we accounted for near alignment, what it may correspond to. But since we're near alignment, if we're really closer and closer to alignment, then like top to charm Higgs, this Higgs to mu tau, tau to mu gamma, these are all heavily pursued. We have not seen them, okay? They would vanish with this approach to alignment. Thankfully, barogenesis does not vanish with this cosine gamma. Okay, otherwise, then it's not so fascinating. So let me give you 2 examples. One thing is a direct production of the exotic Higgs. Okay, so if you look at these diagrams, I have a charm quark and a gluon colliding. This rho Tc that I've shown you produces this heavy Higgs. And the heavy Higgs can decay to Tc or TT through rho TT and rho Tc, okay? Now, if you look at this plot, this is the standard model, okay? Written some time ago just for illustration. These 2, the TT bar is how top quark was discovered in 1995, and subsequently the single top was measured. So now this has been repeated fully, even more at LHC. But LHC physicists have started looking at 4 top, okay? But not 3 top. Why? Because 3 top is even smaller than 4 top. It's a peculiar phenomenon, but it's like some conservation law. But we advocate here because TTT is produced, we have been advocating that experiments should target it because it may happen in this zone. More than 2 orders of magnitude larger. Of course, it can fall below if these objects are heavy, okay? So this is one example. It is also the heavy Higgs search, which is extremely important. Second one, we only worked out fully last week, is that in part motivated by a hint at Bell of beta mu nu that seems a little bit on the large side of the standard model expectation. In this paper, we show that the extra Yukawa couplings, okay, extra Yukawa, I should have outlined that, it can lead to enhancement in beta mu nu, but basically you expect beta tau nu to remain unchanged. So this ratio, the yellow over this light blue, it would be like this, definitely in standard model and also in 2HDM2. This I know very well because, I invented the beta tau nu measurable, if you want. But what we said here in the abstract means we'll break this equality, that this ratio would remain fixed to this up to 2HDM2, but not in this with extra Yukawa couplings, okay? Now, if this hint is true, and we have provided a mechanism, it means it will be with early Bell 2 data, literally in the next several years, can be caught, sorry, okay? Now, the point of extra Yukawa couplings can break this stranglehold, was already stated in this review I wrote with, so Jack's not here, but with Professor Zhang Baodi. Oh, I wonder, Jack was here last week, right? Well, that was one reason to mention the names. It's okay. But this is an important test for new physics, but also really for this extra Yukawa coupling. Now, finally, although it's alignment controlled, I don't know whether you paid attention, but already 5 years ago, there was an astounding result from ACME published in Science of electric dipole moment down to 10 to the minus 28 ECM, okay? And just about 5 years later, very recently, they improved by a factor of 8.6, okay, down to 10 to the minus 29 ECM. So we've been studying this. Actually, we already studied this back in this electric barogenesis paper. But so we took the experiment seriously, but we didn't really take, I would say, this mechanism seriously enough, which we are taking now. And that's why I put it here that it's truly astounding if ρTT can generate baryon symmetry of the universe, the largest extra Yukawa. If this ACME really sounds very good, right? This very good experiment on Earth is actually attacking the smallest extra Yukawa. Okay, my time is already over. Sorry, let me go through this just for conclusion. I would stress a second Higgs doublet is rather likely, and it should have extra Yukawas. It's an experimental issue to check. This extra Yukawa ρTT, sort of a companion of lambda t, or what I later called YT, which is 1, seems sufficient to drive matter dominance of our universe, while the first order phase transition is from this extra second doublet, okay? Alignment can be comfortably accounted for with a second Higgs, because alignment can be used to say that effectively you don't have a second Higgs, but the second Higgs can be below TeV. I didn't go deep into that. Now comes the horror, parameter count. Okay, extra Yukawa couplings conceptually, but we said we have 3 copies, right? So the extra Yukawa coupling is a 3x3 matrix, and they are complex. There's no way to accept symmetry. So each parameter is 2 parameters. We have U-type quark, down-type quark, leptons. So overall 54 parameters. By golly, okay? But most of them are small, okay? But it's not that big a shock. So it's not pretty, it's not sexy, because standard model is not pretty and sexy here. We have 9 masses, 3 rotation angles, 1 CP phase, total 13. Okay, so I put down here, if we increase from 13 to 67, maybe we need a new periodic table, but that takes a lot of work, okay? So this is what is called flavor physics, and I'm a flavor physicist. So let me conclude. We have not seen any new physics. I put an A because I really cannot prove that it is the, okay? So I think it's very likely the next new physics, for instance, is speed to mu nu. And I think it's astounding that it's a very good approach to matter dominance of our universe, okay? So I've given at the last few slides for LHC as probe, Bell2 as probe, and electron-electric dipole moment. And in my group, I've been pushing that we are entering the dawn of a new flavor era. So last but not least, let me show one thing is you saw this thing coming out. Now I have explained from SM to SM2, okay? Standard model, nothing changed in the standard model, but with a second Higgs doublet. So got to find me the second Higgs to take a photo with. Okay, thank you very much.
Well, thank you, George, for this very exciting, inspiring talk. Especially we know where the stock you should invest. So if you have questions.
You touched briefly on the difference in B decay between emitting a tau and emitting a mu. Can your model account for the lepton universality violations that seem to be cropping up at the, I don't know, 3.2 sigma level?
People have tried, and it's not particularly useful.
But can you do it with just with a second Higgs?
Well, the second Higgs has been an early approach, not to the RK star, but to RD star. But you need to really enhance these extra couplings. And somewhere else, something pops up. So it's disfavored, okay? So at lunch today, let me quote, I didn't record it. The chairman said he thinks anomalies would all go away. So if anomaly goes away, it means we don't need such strong tension, okay? But the answer to your question is these extra Yukawas have been used, but unsuccessfully to these anomalies. The RD star anomaly is very, very strong, okay? They're very large, okay? The RK star, because it's a ratio of mu to E, it's okay, actually, let me check, to be honest. What? Please speak on the mic.
RK star is a vector current, right? So maybe you.
Okay. No, RK is not vector. But anyway, I promised Ben to check as well. Okay, well, not to my knowledge.
I think Tommy's comment is correct. So RK and RK star, the Yukawa coupling will not do much. That answer the question. But then you need some current type of that's left-handed gamma mu type of interaction, because that will need to.
Okay. I misunderstood. Yeah, it's the operator structure.
Yeah, that's right. Yeah. Okay, so other investment you want to make?
Maybe I heard it wrong. That you said on a train trip you did a calculation about the alignment, and then you said it's unnatural. But then later on you seem to. Did I hear you wrong?
No. I said from the literature I picked up that alignment means small off-diagonal this Higgs quartic. Right. So I took it as textbook. Howie is a friend and very respectable. So I was not trying to challenge him. I knew this, and I have the formula independently. So on the train, when I am tired of the scenery, I just punched on my, small calculator and just create a table. But just a few entries I found, you can have small mixing angle, even with order 1, this coupling strength. Yeah. So that was a numerical discovery. Okay. On my train trip back, I used my laptop.
So other questions? Well, in middle of your talk, you made one comment. When you really invest all your energy into one, maybe that's the end of the story. So of course, if you hit the gold mine, everything is good. If you don't, what do you take from this type of study?
Well, I already admitted that I'm a fanatic type. I get sucked into something, conviction. So I'm a very bad stock investor unless I'm that famous guy, right? Yeah. Which I'm not. But I think there's a separate aspect. I am not a model builder. So my first paper, well, first of all, I'm invested invested in the standard 2x doubler models, Model 2 and Model 1. Invested nicely with very nice dividends, okay? So when I noticed this change share thing, it was not immediate. It took several years. One day I immediately noticed that nobody mentioned it. I said the top charm Higgs coupling, the top was not yet discovered, but the top charm Higgs coupling is the most significant. So it's like, it's not insider trading, but you jump on a paper because it's trivial, just to make it stated, okay? That's my first investment, whatever that analogy is. But what I argued today was that through a few steps, I started to take it more and more seriously. Originally, it was like I used small money, small change to make small bets. So only after a time I get that conviction to want to jump in. And I'm not going to invest my house on it. Okay.
Oh, okay. So maybe it's on for you one. Well, I think sometimes you need to devote a little bit. Yeah. Right.
Low mass figures possible. Low mass.
Which mass?
Low mass about more than 100 MeV.
100. Huh?
Light Higgs mass particle.
Low mass.
Lower mass.
Figures possible.
I didn't get the question. Which lower mass? And
35 MeV.
what about it?
No list figures.
Just the possibility of having no mass Higgs.
Oh, no mass.
Yeah.
Well, there's almost no mass Higgs called the axion. It's as close to no mass as you can, 10 to the minus 20 EV or something is considered. But you need some symmetry and symmetry breaking to achieve that. Okay.
Yeah. Okay. So
incidentally, since we're talking about light Higgs bosons, so there's a rumor about the 90-something GeV Higgs. Do you have any comment on that?
Why should I comment on that? If it's a rumor, why should I comment? Well, whether it's around 90 GeV or below 90 GeV, it's an endless story, okay? Now, I think the reminder would be that have we done everything correctly? That I would agree with, but
I thought your capital H could be the candidate for that.
no, I think the capital H, we have tried down to 300 GeV, but that already, tickles people because that's relatively low. But I think 300 is not experimentally ruled out, okay? But to go really low, I think you need to start to tune, okay? Put it differently, if you look at the 2x2 matrix that I showed, the standard model Higgs has only one quadratic entry, but the heavy Higgs side has 3 or 4, including an inertial term. So of course they can cancel, but that's work. If you just throw them at random, in general, they should be heavier than the 125, okay? But that's a rough hand waving address to your question. To hit on 90, that's tuning.
okay, so student back there. Well, if no further questions, let's thank
okay, thank you.
Claudia for this wonderful talk.
This 90.